I'm here. Good morning.
Okay, good morning.
So can you see
Welcome.
me?
And we see already your screen, so please
Okay.
go ahead. Please try
So
to keep 15 minutes.
sorry. I will share my presentation. So let me know if you can see my screen.
Let's see.
So can you see my screen now?
Yes, we can
Okay.
see your screen.
Okay. So thank you very much, Bart. So I will now present you rather short introduction on the TSN standards. Just try to get, okay. So I'll start first with a short disclaimer, which has to be, which I have to make you aware, since I'm presenting not on behalf of IEEE, but as just as a contributor to IEEE. So this presentation should be considered as the personal views of the presenter, and not as a formal position, explanation, or interpretation of IEEE. So this is as per IEEE SA Standards Board bylaw, the latest revision in December 2017. So I'm Christophe Mangin with the Mitsubishi Electric R&D Center Europe in Rennes, France. So I've been involved in the design of wireline and wireless networks for the support of quality of service in telecommunication, automotives, and industrial networks for now 30 years, sorry, successively at Nokia, Orange, and now Mitsubishi Electric since 1999. So I'm a member of IEEE 802.1 working group, in particular participating in the TSN task group since 2014. And I'm editor of one of the amendment of one of the standards, TSN standards, so 802.1 CBDB, which deals with stream identification. So streams, you'll get more information about in the presentation. So I will start with some explanation on how IEEE works, and in particular IEEE 802. So TSN standards are developed by the 802.1 working group within the 802 LAN-MAN Standards Committee. So LAN for local area networks and MAN for metropolitan area networks. So it deals mainly with the link and physical layers of the network stack. And this since March 1980, so it's the birth date of more or less Ethernet. More precisely, 802.1 works on standards and recommended practices in the following areas. So 802 LAN-MAN's architecture, the internetworking between the LAN and MANs defined in 802, also 802 security, and the overall network management and protocol layers above the MAC and LLC layers. So the figure on the right side illustrates where the 802 activities, and particularly 802.1 activities, are located in the OSI reference model stack. Now more details about 802.1. So 802.1 is organized in several groups. So three task groups, so TSN, which I will detail later on. Then the security task group, which specifies functionalities to support secure communication between devices. The maintenance task group, which is more an organizational task group which maintains the standards, so corrects the errors that are found in the standards once they are published, or keep them up to date, just to summarize. Then there's a specific group that deals with new standards to be developed, so called Network Enhancements for the Next Decade Industry Connections Activity, or NENDICA. So that's the place where new ideas for new standards can be brought based on the industry requirements. And there's recently a new group that has been formed, which is called Youngsters. Youngsters is in charge of keeping the consistency of the young specification within 802. with Yang being a new, rather new language for the modelization of information models. So now more details about the TSN-TG. So the TSN task group specifies the tools of the TSN of the TSN toolbox, as well as their use for particular purposes. So, which in that case, the task group defines profiles. And the main goal of the TSN-TG is to specify deterministic services 802 networks. So deterministic services meaning guaranteed packet transport, low packet loss or zero packet loss, banded low latency, and low packet delay variation. So in the TSN-TG is the emanation of what was called earlier the audio video bridging task group within 802.1. So that's for the organization. Now some a way to decipher the project names and standard names, because you see there's a long list of standards, amendments, and profiles. So it's like alphabet soup. So you have to find your way in this list. So main standards or base standards are the ones with ending with capital letters. So for instance, 802.1 capital Q or 802.1 capital A, capital B. And then we have amendments, which are modifications or additions of features to existing base standards. So two examples here, 802.1Q CP, 802.1 ABCU. So, and periodically these amendments are merged into a revision of the base standard. So for instance, QBV and QBU have been merged into .1Q in 2018. So normally you shouldn't be hearing anymore about QBV or QBU, but you see, we still talk about them because it's sometimes easier. And the last detail, when you speak about a standard, just mentioning the last letter, it means that it's the latest revision. In the case of 802.1Q, it's 802.1Q 2018. So I come back to 802.1Q. That's why it's used as an example here. In fact, this base standard includes most of the TSN tools specification. So it's a collection of many 802.1QXX. So it's getting a quite big document, and so we will go through it through some of this of its specification in the next slides. So this is the map of all TSN components. So with the green background, you have the list of all base standards and currently developed amendments for these base standards. So they are organized around 4 types of components. So components for synchronization, so mainly relating to time PTP-based standards. So I come back later on this. Components around reliability, latency guarantee, and resource management. So I won't go through the whole list, but we will go into more details of some of them. And at the top, the blue banner lists all the profiles that are defined. So we have a toolbox here in green, and then we have profiles that are defined based on subset of tools of the toolbox, and which can apply to different application domain. For instance, audio and video bridging, mobile network front haul, industrial automation network, automotive in-vehicle network, service provider network, it's more telecommunication, and aerospace on-board network. So what are TSN profiles? As I explained, the TSL toolbox is quite big now, and and in order to efficiently use TSN standards for a specific application domain, you have to define which subset of the toolbox you need. So that's what the profile is for. So the profile allows to narrow the focus and consequently ease the interoperability and deployment of TSN solution for a specific application domain. And it describes how to build a network for particular use, and also gives some indication on how to configure a network for this particular use. So there are some already published profiles. So the original one was 822.1 BA for audio-video bridging. So it's mainly for professional audio and video applications in studio or stage venues where deterministic networking is required for audio. And then the second published profile is a profile for transporting information between base station and core network in mobile networks. And there are 4 ongoing, currently developed profiles. So the biggest one for the moment is the profile for industrial automation networks, which is a joint project with IEC. There's a profile for automotive in-vehicle Ethernet communications, then third one for service provider networks, and the latest one is .1DP in conjunction, so a joint project with the SAE for aerospace onboard Ethernet communications. So on the right-hand side, you have the different steps that are gone through for the establishment of a profile. So usually it starts with the definition of the use case and their characteristics, and then the definition of the requirements that networking requirements that correspond to these use cases. And then the profile is made by mapping a subset of the TSN toolbox to these requirements. And in the end, it leads to the definition of what is required for conformance to this profile. So now the TSN basic components. So TSN relies on 3 types of components in the network. So end station, streams, and bridges. So we have 2 types of end station, the talkers and the listeners. So talkers are the source end station, so the producer of a stream, and the listeners are the destination of the stream, so the destination end station, consumer of the stream. And a stream is a unidirectional flow of data from a talker to one or more listeners. So that these are terms we will find in the next slides. And the bridge, so the architecture of a bridge. So a bridge is constituted of a control plane and a data plane. The control plane is used, as the name says, to control the bridge, and so it's based on the upper layers protocols that can be defined, for instance, in 802.1, and these protocols are used to communicate with external agents, which in fact are the entities in charge of the management or the configuration of the network. Then in the data plane, we have two components, the ports and the MAC relay function. And the MAC relay function includes the forwarding process, so how the packets received on one port are forwarded to another port. And the port themselves are what is above this dashed line is handled by 802.1, and the bottom part of the port, so the lower layers, are specific medium access functions. So famous one is, for instance, Ethernet. So, and then I will go in more details in the forwarding process within the MAC relay function. This is where the TSN. This is where the TSN functions are located. So as I said before, TSN main goal is to provide deterministic service. So what was available before deterministic service was legacy service. So it's based in Ethernet networks, 802 networks. It's based on strict priority transmission, where we can just characterize average latency for packet transmission. So average latency is not enough. As you can see on the we have here, we show here the relationship between delay, packet loss, and latency. So we see that the loss probability decreases with the number of buffers that are allocated in the network. But the thing is that if you want to have a zero loss probability, you need an infinite number of buffers. So this is very difficult to implement. And then we see on this chart that if application needs a bounded end-to-end latency, they will encounter loss. So it's because there's always a case where the latency is over the bound they required. And then this latency can also vary. So this is, latency variation is also known as jitter. And it's very difficult to provide a deterministic service when jitter is not completely characterized. So that's, on the contrary, deterministic service where the target is to have packet loss only due to failure of an equipment. So we don't want any any congestion loss as we used to have with legacy service. And the deterministic service also bring bounded latency. So the thing is that you want to transmit the packet at the right packet at the right time. So that is achieved by reserving resource in the network, and this resource can be buffers and bitrate or bandwidth. And by doing so, you can bound the number of allocated buffer in the network, also the end-to-end latency and the latency variation. So the result is that having zero congestion loss and finite number of buffers in the network, you're able to reach bounded latency. So where in the forwarding process of a bridge, so this is the left-hand side figure. So this is the different stages in the forwarding process. So the first one is active topology enforcement, which are very basic functions that guarantee, for instance, that the packet is not looped on the same port. Then we have ingress filtering. That's a function that checks that packets with the right VLAN and the right MAC addresses are received on the right port. Then we have frame filtering.
Mr. Mangin, can you conclude in 2 minutes, please?
I will try to. Yeah.
Thank you.
So this is the. So I will make it very short now. So this is all the stages in the frame forwarding within the bridge. So, and we see that the TSN is located in this stage. So filtering and police in the flow classification and metering, which happens per stream or per class, and in the queuing frame and transmission selection, the last stage of the forwarding process. So we have different functions. So the first one is per stream filtering and policing. So please have a look at the right-hand side figure to know where it intervenes. So it's used to protect against bandwidth violation and bad functioning and attacks. Decisions are taken per stream or per priority, so they using stream identification. Associated to streams are filters, stream gates, and using the stream identification, priorities are also associated with the streams. And then it's also able to perform metering. So metering is to make sure that a stream fits within an envelope that has been a traffic envelope that has been defined, so that it doesn't consume too much resource. So this is one first function that is at the ingress side of the frame forwarding process. So it makes sure that the streams don't go over the resource they have been allocated. And another TSN feature is asynchronous traffic shaping. Now we are going down the forwarding process. So still using stream identification, this mechanism shapes the streams so that they also fit into the traffic contract they have negotiated with the network. So we have always resource reservation prior to transmitting streams. And this shaper makes sure that the sequencing on the packets is so that all streams get the bandwidth they had reserved. So then we have what is I would say the basic mechanism in TSN. So that was the first one that was developed by the working group. It is specified for streams with very stringent timing constraints, so very low latency. It is located in the last stage of the forwarding process, so in the queuing, egress queuing in Bridgeport, and it uses the basic mechanism is the use of gates at the output of queues. So the packets are just before being transmitted. Packets are stored in queues, and these queues are served based on time windows. So each queue has a transmission time opportunity.
We are at the end of your time window, or at least already double of your time window. So can please conclude.
Okay, sorry. So there's also some other mechanisms here. That this one is also so frame preemption is another mechanism that guarantees the bounded latency. We have a redundancy mechanism that is specified for reducing the loss due to equipment failure. So it's a typical, usual redundancy mechanism over a disjoint path. And then TSN also specifies network configuration architectures. So there's 3 types of configuration architectures, depending on the requirements of the application domain. And then we have also one of the bases of TSN networks is that all nodes, especially for this type of scheduling that is very that is tightly coupled to time synchronization. We have a synchronization protocol that is based on IEEE 1588.2, which is a quite well-known protocol. So that concludes my presentation.
We'll have to go to the next speaker. Sorry. Thank you.
Thank you very much.